Okay, hi everyone. I think we can begin. So this talk is titled Linear Operator Stories from Advancing an 18-Year-Old Data Structure in SciPy. And Lucas Colley will be presenting this talk today.
Yeah, hello. Thank you all for coming. Quick word of warning, there's a lot to fit into this time slot, so I'm going to go very quickly. Please feel free to follow along with the slides on your own device if I'm going too fast. I'm going to try and get through everything. We'll see how it goes. Yeah, just a quick few words about me if we haven't met yet. I'm a maintainer of SciPy and Pixie as well. Have a talk on that tomorrow. Member of the Consortium for Python Data API Standards as well. And yeah, I just finished studying the MCompFil at Oxford. Quick agenda. I'm going to give a little bit of background at the start, then I'm going to try and briefly explain what actually is a linear operator, then I'm going to talk about this kind of enhancement process I went through, what were the challenges we kind of hit, what did I actually do, and then I'm going to try and give you some takeaways at the end, just some like basic things. What did we learn from this? Okay. Yeah, so this work that I'm talking about here, it was part of a project for my master's dissertation at university. I kind of got to choose what to research this year, which was great. So I tried to like find a balance of like my technical experience in SciPy, do something where I knew I could like get stuff done, but also have some research into a new area as well. But another big aim I had, I wanted to kind of produce something that could hopefully be merged into SciPy and be like used by other people beyond the scope of the research. And this linear operator stuff, I was kind of using it for the iterative solvers in SciPy, but it could also be used elsewhere. So yeah, that's kind of why I wanted to work on this stuff. So what actually was the research area? Well, the rough idea that I had at the start was to look at adding two things, array API standard support and also batching support to some of our scipy.sparse.linalg. These two things, other people have been working on them in other parts of SciPy for the past few years, but this was kind of not touched yet, so I thought this might be a good place to start. What is this module? Well, it's a module of linear algebra algorithms for sparse data. A bit more about that soon, but what are these two enhancements? Well, the first one, Python Array API standard. If you've been to this conference the past few years, you might have heard already. I also have a talk from PyData Paris last year on YouTube. You can go and watch. The basic idea is supporting other array types to NumPy. So things like QPy, JAX, PyTorch, also supporting GPU devices, not just CPU. We've been pushing on this a lot in SciPy the past few years. Also other libraries like scikit-learn. So that's a rough idea behind that. The other thing, batching. Batching is basically efficiently solving, or more efficiently solving, many of the same problem at once. This can be like any problem, but you just have a big batch of the problems and you're trying to do it faster than just going one after the other. A common example in like NumPy, you can like add two arrays together. If these arrays have more than one element, then it will kind of do all of the additions at once for the whole batch. And yeah, it does this in a way that's a lot faster than just calculating each one in turn and putting them back together again. Yeah. Okay. I kind of focus my scope in, not on the whole module, but specifically on the iterative solvers. What are these algorithms? Well, what they're doing is solving a linear system, AX equals B, where A is some matrix, B is some vector. You kind of know those in some form, but X is unknown, and you're trying to solve for X. What is the X? In the batch context, this means you have like many of these A, many of these B, and you're trying to find what all of the different X's are. In particular, in this like sparse module, the system may be sparse, and that just means that A might have very few non-zero entries, so it's mostly empty. And this kind of problem comes up a lot. And for that kind of problem, you want to use like specialized data structures that are efficient for these sparse kind of matrices. Or alternatively, you might not even know its concrete elements at all. You might just have A represented by what it does to a given vector. And it turns out there are lots of algorithms based on just knowing what A does to a vector for solving this kind of problem. Okay, and yeah, there are lots of these different algorithms in SciPy in this module. The iterative part, specifically, these solvers, they just start with a guess for X, and they iterate through Each iteration, they try and do some kind of computation to better approximate to x, and they just keep going until they've kind of found a solution or fail. Okay, and this is where linear operator comes in. Like I said, we want to support these like sparse data structures. Also, if we just have like the abstract representation. And before adding these enhancements to solvers themselves, we need to add it to the data structure underneath. Naively, I kind of thought this was the quick first step. This wasn't really what my research was about. It was just kind of a necessary thing to do. But of course, it takes longer than you expect. And yeah, that's what we managed to get a whole talk out of it. Okay, what actually is this data structure then? So it's an abstraction over these matrix-like objects. You have like 2 dimensions, can be square, can be non-square, can have complex elements, real elements. But crucially, they have these like associated multiplication functions. So you know, what do they do to a vector? What do they do to a matrix? And yeah, this is linear algebra, so you can combine them in lots of different ways, and you're going to get some new linear operator out that does different things to a vector or a matrix, but it's all definable in terms of the input. And in code, how is this actually implemented? Well, this is a class that's available in SciPy. It was originally contributed 18 years ago. It's kind of stuck around since then. Hasn't changed too much since then, but it's changed a little bit. There's a function in this module called asLinearOperator, which can give you one of these, convert from like a dense array or a sparse array. You can also construct one yourself in various different ways by kind of giving in this function of what does it do to a vector. So what were the requirements for my work to like get started on my research? Well, we want to be able to represent batches of operators that have this like extra b in the shape. That could just be like a single dimensional batch, just like a stack of them on top of each other, but it could be multi-dimensional as well. And this could be like 5 times 2 times m times n, something like that. And yeah, we want to be able to input and output with these to kind of represent our problem in it, but also to do the actual computation with them as well. This kind of required removing any assumptions of 2D data, generalizing out, and also for the array API part, generalizing out from any operations that are specific to NumPy. And crucially, we had to do this without breaking the world, because a lot of people use this stuff in SciPy, and I can't like break everyone's code just for my little research project. That'd be pretty bad. Okay, so what actually happened in the process? Well, I started a draft PR in October at some point, kind of very quickly already had a prototype working with the kind of examples I needed. Thought, great, get it merged in a week or two, something like that. But yeah, that wasn't quite how it worked out. Input, output, this part wasn't too hard. There were a few places where we did literally just hard code the dimension to 2, and kind of removing that got us a lot of the way. In other places, we were kind of referring to the shape, like assuming that the last 2 dimensions are 0 and 1. Maybe if you, all we had to kind of do there was refer to the last dimensions with negative indices. So that was not too bad. For the array API stuff, how did we generalize from NumPy? Well, this also wasn't too bad in a lot of places. We kind of introduced a new parameter to pass in an array namespace, saying this is the module for my array, so you can pass in your CuPy or your PyTorch, and then we kind of just store this in a private attribute on the class. And then in other places, we can use that instead of using NumPy where we were before. And yeah, there were some simple swaps, a bit of change of syntax in places, but this also wasn't too bad. What about the batch computation? Well, this also wasn't too hard because NumPy has kind of solved everything for us. We don't want to reinvent the wheel and kind of do batch computations in a way that other data structures don't do it. We just kind of want to follow what the rest of the world is already doing. And because we're using these array operations underneath, we kind of get a lot of this stuff for free. We just need to be very careful about when we're messing around with arrays, when we're like pulling out columns and passing things through, that we're not assuming things are 2D anymore. One way that you do this in the code is, for example, using this ellipsis indexing. In NumPy, this just means you're referring to like arbitrary dimensions, saying I don't want to touch those dimensions. I only want to touch these 2 dimensions at the end that I care about. So yeah, again, not too hard there. But now we get into the challenges. So kind of the number 1 challenge that I had, kind of alluded to it already, is backwards compatibility. We can't just break people's code because I want my cool new batched array API stuff to work. And in particular, if the user's provided matvec function assumed that the data would be 2D, like it may well have done because that's all that was supported beforehand, we can't suddenly break that assumption now. So actually, if we could break that assumption, then you can implement this matrix multiplication a lot more efficiently or a lot more simply in terms of matrix vector multiplication by just doing 1 batched matrix vector multiplication. But yeah, we can't do that, and kind of learned the hard way through the test suite that you can't do that. Another slightly more complicated backwards compatibility constraint was picklability. You might have heard of pickle. It's a way to like serialize, deserialize Python objects. Again, the test suite caught this, that we were breaking that. Why? Well, you can't store Python modules on a Python class and pickle it. You need to find another way of doing that. So instead, what we do is we store like an array from that module. We tell pickle this is how you like represent that in your serialized state, and then we tell it also on the way back out. You can then on that array apply array namespace and grab this self._xp that we want. This is a pattern that's now kind of repeated in quite a few places in SciPy where we have these array API classes now. Another challenge was like poor documentation. Really, there was nobody else working on SciPy who was an expert on this. So I was kind of getting into it, trying to like become the expert on this code with nobody else to talk to, just like me and the code and the Git history. And yeah, there were not many like doc strings like on internal private functions, not many comments. This kind of stuff would have been very helpful for me. I was basically trying to like figure out, like get in the heads of the people who wrote the code. What were their intentions here? And you know, maybe it's easy to be uncharitable and think that whatever they're doing is just buggy, but actually maybe it's you're misunderstanding it, and actually they did it deliberately. So yeah, that was something I had to spend quite a lot of time on. Also improving the user-facing documentation as well. Another challenge was like finding some like maybe bad decisions or decisions that were okay in the past but didn't make sense anymore. In the 2D only case, it was actually supported for the matvec method that you could pass in like row vectors or column vectors. For convenience, the interface would handle all this for you. You didn't really have to worry about what shapes you were passing in. That's all well and good, but actually, when you have arbitrary batch dimensions, this is kind of complexity and ambiguity that we really don't want. So we actually made the decision to deprecate this and say, no, we're going to remove this capability from SciPy, break your code eventually. Deprecation in SciPy means that we don't just break things immediately without warning you. Instead, we emit a deprecation warning for 2 minor releases, which is roughly about a year in SciPy's timeline, and say, okay, if your code uses this, it will break at some point, but here's how to transition away. In this particular case, we could just tell people to use mat instead of matvec instead. So hopefully this didn't bother too many people when they saw that warning. And yes, we got there eventually. This particular PR got merged with only 248 review comments after 4 months of iterating. And I mean, I've kind of told you the whole thing in 5 minutes. It might seem, how on earth could this like relatively simple thing have taken so much? Well, a lot of the work was really in testing and in documentation. Kind of the existing tests and docs were not great. And when you're having to figure out from scratch what should the tests be for this stuff that was actually written 15 years ago by somebody else who was in a completely different frame of mind, yeah, that's not the easiest thing. Also, there were some bugs that needed fixing. Okay, what did we learn from this? Well, the first thing is that established code can be like bad. That doesn't mean that it's not useful code. That doesn't mean that you know, it's not still very good for the world or been very helpful to a lot of people. But yeah, established code that's in SciPy or that people have been using for 20 years can be like unloved. It can have people who've never really bothered to write nice documentation for it, write nice tests for it. I mean, I don't know what the actual origin story is here, but it's perfectly possible that like a small prototype that somebody had just kind of accidentally became widely used in the world. So you have to be kind of careful of putting like too much trust and reverence on these things. Also, in a big open source project, incremental improvements can come along over time. Somebody might just drive by, make a little change that makes sense for their use case, and then leave, and you never hear from them again. That can be good, but sometimes it can introduce inconsistencies as well and make it much more confusing for somebody else coming along and trying to figure out what it's doing. Okay, also, as I mentioned, backwards compatibility is very important. Maybe if you're not working on SciPy, if you're working on a smaller library, you might think it doesn't matter so much. But I think you still have to remember that if there are people using your code, they probably care a lot more about it keeping working than whatever brand new feature you're working on. So yeah, don't underestimate the importance of not breaking people's stuff for no reason. It's not always clear exactly what this means, though. Like when there are bugs that you're fixing, like clear bugs, okay, probably they're going to be happy you're fixing them, but that can still break their workflow if they were kind of relying on those bugs. So yeah, you kind of have to judge what is the contract between the API and the users. Few things I'll kind of skip over for time. Refactoring can be very useful. Testing, also very crucial. You want to kind of figure out what tests are missing, not just get the existing tests passing. And yeah, we in particular for here, we used a lot of like systematic tests with random data, a heavy use of pytest.mark.parameterize. You can check out that PR, but it's a lot nicer than what was pre-existing. And also write good documentation, not just for the users, but even more importantly, maybe for yourself to make sure you know what you're working on and you're not having misconceptions. I had lots and lots throughout this process that like I figured out I was wrong and kind of relearned what I was doing. It's very helpful for that. And also for future developers, make the next person who has to touch the code in 10 more years, make their life a bit easier than yours was. And finally, kind of don't underestimate the easy work. It was certainly tempting at points in this process to just like leave it, say, I don't care about getting this into SciPy anymore. I just want to do my own research and my prototype is good enough. But I think, yeah, there can be a lot of pressure on you, but if you do have the time to kind of get stuck in and try and create some solid foundations that can be reused by others, definitely go for it. If everybody did that, and if the people, 10 years ago or whatever, whoever last touched it, if they did that, then it can have a big, like, positive knock-on effect. Yeah, thank you for listening. Thanks especially to all of the reviewers involved in the PRs discussed here. Wouldn't have been possible otherwise, especially Matt Habelen, SciPy maintainer. He spent a lot of time on this working through that with me. Also, Patrick Roddy for this talk template, and the organizers and volunteers of EuroSciPy. Thank you.
Thank you. So I think we have a few short minutes for questions. Is there any question? Here.
Thank you for the talk. You said at the beginning this was supposed to be the easy first step before your actual research project. Do you want to talk a little bit about what your actual research project was and whether you got to it or were distracted?
Yeah, you've unlocked the secret bonus slides. I promise this wasn't planned. Or maybe you saw the slides already. I don't know, but we'll pretend not. Yeah, so how is this used in the solvers? Every single line here is like a different system, AX equals B, and this is kind of solving them all in parallel. We're tracking like the residuals, so they want to get down to the bottom here. This is when it's solved, and you can see they like solve them at different times. Some of them only take 15 iterations, some of them take a bit longer. But this is all done in parallel at once, kind of using a single batch linear operator rather than lots of different ones, and that kind of simplifies that a lot. We kind of benchmark this using n-dimensional sparse arrays in scipy.sparse with COO. for if you have a massive batch of these problems and only like a small kind of size of arrays, this can give you a big speed up. And also the big thing is memory. On alternative, if you have big problems and a large batch, it can be a lot more memory efficient to operate on these in one go. So yeah, this stuff isn't quite merged into SciPy yet. It's still in an open PR. But yeah, it was nice that this kind of worked enough to get a research project out of it. Yeah.
Is there any question? Yeah. Okay, so last question, because we are slowly running out of time.
Yeah, thanks. So I have a bit of a big data question. So you already, showed some improvements, and I guess sparsity, of course, also keeps memory low. But is this also, or I don't know, in research, are you also tackling problems that are larger than what you can fit into memory and thinking of, tools like Dask and out-of-memory support, or is that a little bit beyond what you were thinking of?
Yeah, so with Dask, we have got some support in SciPy via the Array API. Generally, if you need like specialized algorithms for out of core, if you have things that just fundamentally don't work so well, if you don't give them special treatment, then we're not kind of doing anything special for that. But I haven't really tried using this with Dask, but if it's one of those things where just having things in Dask arrays already helps a lot, then this should actually work with that. So yeah, it would need somebody to look into it properly. But yeah, Array API is one of the ways to make progress there.
Okay, so thank you so much. Now we have 10 or 9 minutes to go and change the room. If you want to stay here, you can stay here. And if you want to stay here and still have a few questions, you can ask here our presenter. Okay, I think we can slowly start. So this presentation is titled Using Python for Satellite Operations, a lesson from the MOVE space mission. And the presenter is Lawrence Broadley. Yes? Yeah. So good luck. Do you want me to tell you if it's like 5 minutes? Yeah, okay, I will just raise my hand.
Is that better? Yeah, we're a small company that's trying to change how scientists access astrophysics research data by building satellites smaller and faster and cheaper than typical multinational space agencies like the European Space Agency would build a mission. For most of my time with the company, I've been doing simulation work, so looking at our orbits and instrument performance. However, for the last year and a half, I've been working on a Python application called MOVE, called Maestro, which is flying on MOVE, which is looking to aim to improve the pointing performance of the mission itself. So this is a nice render of MOVE. It's a small satellite measuring in 20 by 20 by 40 centimeters and weighing about 25 kilograms. It was launched in November last year on top of a Falcon 9 rocket into approximately 500-kilometer sun-synchronous orbit, which means it passes over both poles every time it orbits the Earth. And on board, it has a UV and visible detector. The scientists that are signing up to use MOVE are really interested in looking at how stars vary over time in those wavelengths. They're really lucky. They're hoping to catch a flare, so a massive release of energy in one go from the star. It's built by a Hungarian company called C3S, and the pointing hardware was sourced from a Dutch company called ISIS. So due to the nature of the mission, which is deep space astrophysics, we're really keen to have very good pointing performance. So over a 30-second period, we want to look no more than 20 arc seconds away from where we're trying to look. And the reason for this is we want to avoid poor performance having a negative impact on our scientific results. So this is some made up results, but this might be what you could potentially look at when you're looking at a flare. So 1 is like the average amount of light that would come from that star. So you might have a situation where you shoot up to 140% of the light you would normally get, come down to 80%, and then go back up. What we want to avoid is something that's happening in this bottom plot, where you get spikes that randomly happen that look like it's lowering the amount of light. And that might just be because the satellite is looking, but it's shifting to and from the satellite, from the star. And we want to avoid a scientist coming to fit a model to this data and getting to this point and thinking that, oh, the dimmest the star gets is 75% of its normal mean, when that's not true at all, and that's an artifact produced by the satellite. MOVE does have some hardware to help do that. So the big red disk is the telescope itself. The 2 smaller disks are called star trackers. These are like mini telescopes that can effectively fingerprint where it's looking in the night sky and tell the satellite to point either in a more correct position or to stay looking where it's currently looking. However, this is not always a perfect solution, and there are a couple of reasons for this. So the first one is you can have misalignment between the star trackers and that telescope boresight. Obviously, we measured this on the ground, and the software can account for this, but then you stick it on top of a rocket, and it vibrates a lot on its way to space, and this misalignment grows and is not what you expected. So you might have a situation like this, where you think you're pointing dead at the star, but actually you're pointing where that purple dot is. You might not notice this because that purple ring is the diameter of the telescope, so you're still going to see the star, but you're not exactly aligned to where you think you are. This is a small impact. Again, this is like maybe an arc second or 2, but it is noticeable. Then when you're in space, you're going to start orbiting, and the star trackers are constantly updating where they think they're looking, and you're going to start shifting the center of the boresight around a lot. And that's what's happening here. This is a made-up example. You get a random walk of this high-frequency jitter, and every time the ring flashes red, that means you would have potentially lost the star for that moment. You then get some longer more periodic features. So this is sped up, but this would happen over the course of an orbit where you drift away from the star and then back towards the star. And this can happen for a number of reasons, but the main one is something called thermoelastic distortion, which is basically as you go behind this Earth relative to the sun and then come back out, you have a massive temperature change, and that will cause the metal inside the satellite to either contract or expand, which will further shift this misalignment that was static and cause this drifting behavior. This is made up, but it's just to show what's happening. This we expect to be around 100 arc seconds, so quite a big amount of pointing that we have to deal with. So the star trackers are great at telling us where they think they are, but what they can't tell us is if we're actually looking at the star or not. But the detector is, funnily enough, wonderful at telling us if we're looking at the star. So the engineering team at BSSL came up with an algorithm that would use the detector to help inform where the pointing is going. And this is called our payload in the loop, or PITL algorithm. So here we have two situations. In the first one, we've taken a measurement and the star is nice and inside our telescope diameter. So we can get a really high number of counts and be really happy with that. And we can carry on taking measurements in this situation. In this bottom one, the star is slightly outside of our telescope. And we won't see no counts because you'll get stray light from the sun, from the Earth, and the detector itself will be inherently noisy. So there'll be some level of readout. But it'll be drastically different to what was happening in that top situation. So we know now that we need to try and find the star, and we're going to use the detector to do that. So what we'll do is we'll do a search pattern. In this example, we can do a hexagon, but we have the ability to make it any polygon that we want to do. So we move to a position. So here we've moved slightly to the positive x-axis, and we're going to take a measurement. We'll check at the end of our search, and we're not, so we'll carry on until we've done a full hexagon around the central point that we were originally at. We'll look at the measurements that we got during every single one of these positions and compare them. If all of them were at that really low level, we'll go, we haven't found the star, we need to try again, and we'll increase the size of our search area and look again. But thankfully, in this example, the star was nice and captured in that first measurement. So we can say our new pointing position has to focus where we were there. This is our PITL algorithm, and we went to C3S and we said, we want to do this. How can we have this on board on the satellite? They said that we had to write it ourselves. We could do it in C, C++, or Python, and we had 6 months to do it. I'm a Python developer. I don't know C or C++, and I didn't fancy trying to learn those in 6 months while writing mission critical software. So I've written it in Python. Like any software development project, we had a couple of challenges, things we didn't expect, things we did expect that made it a bit more difficult. MOVE is not C3S's first satellite, and they already had pre-existing software that was a custom Linux distribution designed for embedded systems that had Python 3.8, but they were trying to update to a new distro and give us a newer version of Python. Unfortunately, they weren't able to finish that in time, so we got told we were going to be stuck with Python 3.8. Thankfully, this wasn't actually a huge issue. I was a little bit worried at the start, but there was nothing massively impactful. The only real cost of this was a couple of hours of development time whenever I would forget something that didn't exist in Python 3.8, like trying to natively read in a TOML file. The bigger issue was that because it's an embedded system, you can't just pip install any package you want. You have to have something called a Yocto recipe. If you want to use a popular package like NumPy, these are readily available and it's really easy to install. What we wanted was something a bit more niche called SGP4, which is like a satellite position propagator. And there is a Python package for that, but it's not a particularly common or well-known one, so that recipe doesn't exist. So we had to use up some of C3S's development time to backport that and have it available for us if we wanted to use that. The other thing that we faced was scope creep. So at the start, we wanted to just run this algorithm after every measurement was taken and then make some decisions based on that. But to relieve pressure on C3S, we started to expand what we needed to do. So now we were going to initialize every measurement, take every measurement, save it, make the decisions, send the commands to point it. So that grew, and made me more glad that I was writing this in something that I knew and was aware of. And then the next thing that that whenever you tell someone you're doing something in Python, that they will probably ask you is, but isn't Python really slow? Do you really want to use that? And the wonderful thing about satellites is they have a huge amount of overheads, and you can make use of those overheads to not have everything running lightning fast all the time. So if you want to take an hour's worth of observations of a star, no scientist is actually going to be like, well, it's going to take an hour of my time. They know that it's going to take more than that. So if you're pointing in the back corner of the room and you now need to be pointing in the far corner of the room, it takes you time to move to there. If you've been in a position where you've been depleting your batteries, you might need to charge them. If you've just done a really long observation, you might need to download data to make more space on board for these new observations. And this all builds and adds on to the amount of time that your satellite is going to take to do your measurement. So your hour-long observation might end up being an hour and a half. So when we're starting up our application, we're reading in files, validating those inputs, and then likewise at the end, when we're saving, we're shutting down. That not being the fastest thing in the world is not the end of the world at all for us. It just becomes part of Move's overheads. And the other benefit is when you're worrying about timescales of hour-long observations, it taking an extra couple of seconds to start up is not that impactful on the overall life cycle of your mission. There are obviously some situations where you want things to be a little bit faster. So for example, when we realize that we want to do a search, the faster we can execute that search, the faster we can get back to pointing in a good direction, and the more and better science we can be doing. So that's where native Python is maybe a bit slower, and NumPy will help improve performance. But again, here we're talking milliseconds, when if you're doing a search that's got 8 points in it, that's 8 5-second integrations, 8 6 seconds to point to each part of that hexagon and settle. So again, milliseconds is not a huge impact. So on a satellite, time is actually your friend, and not being lightning fast is not the end of the world. When we came to test this, we start with some very standard bog test unit and integration tests in PyTest. There's nothing particularly exciting about what we do there. But what we do after that is some local mocks where we have a bit of code that pretends to be the satellite. We'll send back messages, receive messages, send data. And we tend to run 1 or 2 of these for each new feature we develop. So these are very long running tests. They'll be on the order of minutes. And they're basically just to make sure that we catch any bugs before we send off for hardware testing. And they start to inform what our hardware test results should look like. So after that, that's the end of anything we can do locally. And then we have to start shipping data to C3S and ask them to run things on the hardware. So the first step is engineering model tests, or EM tests. This here is a picture of what a satellite looks like before it's constructed. It's called a flat sat. This main box here in the middle is the onboard computer. The black box at the back is our detector, and then attached with the blue wire is the computer that controls the pointing system. So here, this is the first time that our code will interact with the hardware itself and make sure we can actually communicate, send the right messages, receive the right messages, that they're doing the correct thing, behaving in the correct way. These are probably the most important tests that we run at any stage during it, because if it can't pass here, then it can't go onto the satellite. And they work very well with the local mocks because we'll use the same configuration files for both and try to ensure we get the same results out for both. Pre-launch, we got to test on Move itself. I would love to say this is me in the clean room, but it's not. My testing is sitting in an office looking at log files. But it's still a very fun part of the testing, because this is where you get to ensure that you work on the actual hardware that's flying. Obviously, we don't expect any differences between the EM and the flight model, but there's always a chance that something somewhere is slightly different. And so this was very useful testing. We were also able to fit in with the end-to-end testing for the rest of the mission, which allowed us to run some much longer tests. So we're able to run for like 12 and 24 hours continuously to ensure stability, and the results were as expected. Now we're in orbit. We unfortunately don't have that nice ability to test on the real hardware. So we have to sort of hope a little bit, but it's not entirely just hope and pray if the rest of the testing has gone well. The other thing that we do have is full onboard redundancy. So we have 2 onboard computers and 2 detectors. So what we're able to do whenever we need to make an update to the code now is upload to one half of the satellite and run a single observation using this update before switching to the other half for any other observations that we want to carry out at that time. Then we're able to download the results and ensure that they were what we expected. And if we're very happy, we can upload to the other side, and all observations going forward will use this new code. And if not, we know we need to go back and try and make some changes. So like I said, we launched in November last year. And due to the nature of the orbit, you can talk to the satellite 3 times in the morning and 3 times in the afternoon. So when we scheduled it up for lunchtime, at the first running of Maestro, I knew I was in for several hours of being very nervous, waiting for our results to come down. But when they did come down, it was very positive, and we were able to get very good results. It ran exactly as we expected in that first situation, so we were very happy with that. As commissioning went on, we tried more and more ambitious things. We tried to use this code to correct that initial misalignment that we had. And during that stage, we found a small bug. One of the input ranges should have been -pi to pi, and it was 0 to pi. But if anything, I'm actually really glad we found the bug, because that's a 2-character fix. But it does allow you to go quite nicely through that pipeline of full testing and deployment and make sure you're happy that that's working before you try any larger, more complex updates. Algorithmically, whether or not it worked is up for debate. It does work quite nicely, but there are things that we want to change and improve. So one of those improvements one failed measurement. We now need several consecutive failures before we trigger that. And this here is an example of one of the measurements that we did post that update, and it illustrates why we've done it. So along the bottom, you'll see that initially we've got very low counts and we're unhappy with those. Anything below that red line is cause to start a search, and anything above the green line means that during a search, if we get a result there, then we've probably got something that is signal and isn't just noise, and we could potentially move in that direction. So we start off our observation and we get several failures, and then we do our search, during which time we get one nice, really high point. This is like an ideal situation for a search, because it indicates to us that there is one direction we should definitely be looking at, and that's where the star will probably be. So we'll have pointed in that direction, and then as you can see, we get nice high counts roughly at that level for the rest of the observation, apart from one tricky point which drops below that red line. And when we're on the ground, it's really hard to determine what's caused this. This could be the slight off point that could be caused by a small glitch in the pointing system. It could be caused by variation in the star. On board, we can't determine what that is. On the ground, when you look at something that's not a time series, you might be able to. But as you can see, if we had done the search here, we would have lost the next, I think in this observation, we were doing 8 points during a search. So we would have lost the next 8 frames to search when we didn't need to, because we've already automatically corrected and are pointing in the right direction already. So this was one of the much larger changes that we've had to make to the algorithm. And I'm glad it came after the small bug, because it was far more fundamental, but it deployed well and is now working, as you can see, as intended. We've got a couple more changes that we want to make algorithmically. So I said that we move in the direction of the largest number of counts, which here is very good. You've got one which is clearly higher than the rest of them, but that's not always the case. In some situations, you'll see 2 or 3 that are very close together, and one of them is just naturally higher because of a random number of counts was higher because you've got slightly more noise or the star was slightly brighter. So we're looking at trying out different methods to determine what the direction that we should actually move in is. So what I'd say that the main things that we've learned from this is that Python is a super useful tool in developing space missions. So Python's been used in MOVE throughout its development lifecycle. So like I said, we've done its orbital analysis and orbit selection using Python. We did instrument performance simulations. Our data reduction pipeline will have Python sections in it. And I think it's very clearly here in Maestro where Python shows that you can help space missions achieve mission success using Python. I would like it if Python could work a bit more seamlessly with embedded systems. I mean, I'm not an expert on that. I don't really know how that works, but it would be a bit nicer than having to rely on manufacturers telling me what I can and can't have package-wise. And then the other thing I'd say is that if we were at a satellite conference rather than a Python conference and this talk was just presenting the idea of the algorithm and I wanted to know what to do it in, many people would tell me C or C++. One of the potential manufacturers we had for MOVE, in fact, told us that they could only support development of applications in C++. But I think what we have shown with Maestro is that Python is a very useful tool and it can help you achieve success with satellite missions in languages that the industry might not expect. It's now been running for several months. It's taken hundreds of observations, none of which we've had a problem with. It's not negatively impacted performance. So we're very happy that we chose Python because it's helped us develop mission critical software. Thank you very much. I'll take any questions.
Is there anyone who wants to ask a question? Yeah, okay.
Yeah, thank you. It's probably a very basic question, but I was wondering, is one satellite only tracking one star, or was that just an example? Is it actually tracking multiple stars in one view?
So we have a really small field of view, so we usually hope to capture just one star. There are some that are close together, and we try to suggest to our scientists that they don't look at those. We have had one case where we've done this with a really bright background star, and we have noticed that we did accidentally lock on to the wrong star. So it is a problem that we have to face.
Okay, thank you.
Just one quick question. You said that you fixed a bug. Was that in the live system? Did you just up?
Sorry. Can you repeat that?
Did you? So you said that you fixed a bug in the software. Was that while it was running on the satellite? Did you just upload a new release to the satellite, or how did that work?
Yeah, so the application isn't running all the time. The satellite will turn it off and turn it on. So yeah, we just when it's not running, we just upload the updated .py file and it runs.
Any more questions? Yeah, okay.
You may have covered this already, but regarding the point about embedded systems, I know there's another talk about MicroPython and CircuitPython, and those, I know those things exist. That's more of a comment. But could you maybe elaborate a little more on where there are a lot of challenges of using SciPy with electronic systems and or satellite systems, I guess? Could you maybe comment on that?
So not really for us. So relative to some like smaller satellites, we have a relatively powerful chip and a large amount of memory. So we're never really hitting the boundaries of having to worry about switching down to like MicroPython, for example. Yeah, the only real issue is you might not have your package available. So you can't pip install because you need the software on board to ensure that it's going to work with the chip architecture that you have. But as long as you can get a recipe, which not going to lie, I'm not an expert on that. I don't know how they're created or how they properly function. But as long as you can get that to run, then we didn't really face any issues.
Any more questions? No? Okay, so we are ahead of time. So if you have any more questions and you don't want to ask them here publicly, you can go. I'm sure our speaker will gladly give you an answer. So now we have a coffee break. Okay, next session is going to be, I think, 3:20. Yeah.
Yeah, you can test it.
Yeah, hello. Yeah, can you hear me? Should be fine.
Okay, let's give 1 minute to gather around. I think maybe you can just close the door. Maybe someone will, someone will notice and come here. Or we can tell everybody that it started. Yeah, you can. Yeah.
All right. Does this work?
Okay, so I think we can start, and probably maybe someone can also join us. So please welcome Diego Rodriguez, right, with his presentation about finding the right ROR. Thank you. Yeah, welcome.
All right, thank you, everyone. So, my name is Diogo, and I'm here today to talk about finding the right ROR. And before that, I'm going to talk about what is MDPI, what is ROR, and what ROR means for the publishing industry. So, my name is Diogo. I'm a data science lead at MDPI. I have a bit over 8 years of experience developing and deploying AI-powered solutions in the areas of NLP and computer vision. And MDPI is a publishing company based in Basel, Switzerland, and it's an open access publisher. So as open access, it means that you can read for free all the published papers that MDPI publishes. And the mission of MDPI is to advance open science, and it's, as any other publisher in the industry, is committed to the industry standards, transparent metadata, and open tooling. So for example, for standards, it means that in publication ethics, it corresponds to the COPE standards and the STM integrity best practices. It uses persistent identifiers such as ORCID for author identification and DOIs for manuscript identification. And relating to institutions, it uses ROR. And it's by default open by default company. It means that has a strong preference for open source tools, and that includes ROR. So ROR stands for Research Organization Registry, and it's a global and community-led open source data registry, and it registers institution information. And these institutions can be private or public, and these can be either from universities, hospitals, funders, or even private research organizations. It's, as I said, openly available, and it's free to access by whoever. And it's led by a community. Multiple companies led this initiative, including Crossref, which is a renowned company or non-profit organization relating to the publication industry. So why does ROR, it's kind of important for the publication industry? Why does it matter? So this registry has really valuable information relating to research institutions, such as, normally the name, information such as where is the city based, where the country this institution is based, and some other information like normal aliases that are used. So for example, MIT, you can refer to MIT or Massachusetts Technology. And for example, in Switzerland, there are 3 official languages. So it means that you can, officially name any institution in 3 languages. So Italian, French, or German. And basically, the registry has and holds all of this metadata that is quite valuable. Besides, there is also relationships between these institutions. There are multiple levels of institutions. So one institution can be part of a larger institutions, so they have also these connections. And for example, ETH and EPFL, which are two renowned universities in Switzerland, they are related to each other, even though they are not, father-son relationships, but they are working, or a lot of times they are working together. So as an example, there are here 4 real cases of one institution. They come from 4 published papers, and it means that you can see all of them are relating to the same institutions. They are written completely different, so there are 4 distinct name variations of these institutions, and using ROR we can actually map to these 2 institutions. And the first one relates to laboratory or physical chemistry, and the second one, it's relating to the ATH. So all of these 4 as these 2 institutions in their naming that we can map to it. So without this shared ID, which the registry provides to us, every publisher needs to create their own registry, and community-led initiatives generally, because they are larger, they are generally better than one company actually putting money in to create their own registry. So there is, MDPI adopted this registry and these ROR IDs, and it's simple because we can, improve affiliation-driven data. It means that we can, when we publish a paper, authors give us their affiliation as a sort of string, and then we can map these strings into these IDs and then drive analytics on top of it. So we can actually, create reliable reporting, such as we can answer simple questions on who is publishing at MDPI. Is this institution publishing more with MDPI, or it has been fading away in the past year? So this is quite relevant information for multiple teams at MDPI. And there is also better metadata quality. So MDPI shares a lot of metadata about the articles that it publishes with, for example, Crossref and other funders and other institutions. So having this common identification or identifier about the institutions that they are publishing with us, it's quite relevant. So I think that's why you joined, is why, or how is MDPI actually finding the right ROR ID? And we have come up with a solution that it's based on 2 pipelines, or there is 2 parts of our solution to find the right ROR. There is the first part, which is the automated data pipeline, which is this first block that you can see here. And then there is the inference pipeline. The reason we went for this architecture is because the registry is updated on a monthly basis, and sometimes even twice a month, with new institutions or even corrections to existing institutions. So because of this fast changing data, we couldn't create or train just a simple classifier to map names to IDs. So we had to decouple this understanding of the data and map this understanding to IDs. So the first part is this automated data pipeline. It runs every day, so it's quite simple. There is this, we have like an Airflow pipeline that just checks whether there is a new ROR file that was published recently by the registry. If yes, we download the necessary files, and then we process and embed the records. So here we will go a bit in more detail what this means, and then we create a quadrant collection. So Quadrant is a vector database tool that we use. It's also open source. And secondly, there is the inference pipeline. So it means that a system or a person can submit 1 affiliation strings. We have a name entity recognition model we train in-house with a proprietary data set that extracts information out of these strings, and then we embed and do semantic search based on this information that we that we captured from the affiliation strings, and then in the end we can actually perform the match and return the results. So in more detail, how do we do the first part of the pipeline? As I was saying, that we fetch the latest registry, we download the file, and then this is the important part, is the index of each name variation. So as I was saying, the registry gives us names, aliases, acronyms, labels, multiple different ways to, refer this institution, and the city and the country. So we actually take all of these name variations, and then we embed using a embedding model, an open source embedding model. We embed these names, and all of these names actually, with and without the city information. So in the end, if there are, multiple names and multiple cities, it means that we will create multiple embeddings for the same institution. This will give us the variability that we are searching. When we do the search, we are able to allow the user to insert any type of formatting in their affiliation string. Then we do some filtering, because there are some withdrawn and inactive entries in the registry. There is one important aspect, is these inactive, sometimes they have successors, so they were replaced by new IDs. So it means that we would just take those names, those ways of writing these institutions, but we will map them to the successor IDs. And then we will just, when there is a new registry that, or there is a new data that was uploaded to the registry, the way that we deploy this to production is very simple, because Quadrant allows us to create a new collection that we use for search, and we just swap the aliases. So we just swap the name. It means that in the production, when we release a new vector collection to production, we just say, all right, this is the new collection we use by the backend. So it means that updating the system is a zero downtime. So it means that every time the registry releases a new data file, we can update our system without any retraining or any really effort. Then there is the inference pipeline. And for that, there is the user passes a string. There is this name entity recognition model that we trained. It's a very simple one. There is only 4 entities, which is organization, sub-organization, city, and country. So we use these entities that we identify in the string to then create our potential search pool for that string. We embed with exactly the same embedding model that we used to create the vector representation. And then, vector search, similarity, and we retrieve the top N similarities. There is a bunch of business logic associated to it. So for example, if the string doesn't have the country and has the city, we have a city to country mapping to extend our search performance. Also, countries are expected and cities are expected to have in a certain ISO formatting. So we also do that kind of mapping. For example, Turkey in our registry is actually Turkey. So we need to do these kind of mappings to make sure we retrieve the correct institution. And this is because sometimes you have this generic naming, such as, University of, maybe I'm making things up, but there are a few organizations relating to states. So you can have things like, Department of Biology or something like that. And if you don't have the country, you make bad matches. So when we are actually doing this final part, when we are actually doing, the number 4, which is the vector search, we always try to make filters that lead us to the correct institution, rather than just letting the embedding do the matching. So that's the 2 parts pipeline. Our system actually wraps all of this logic into 2 endpoints, so 2 ways to extract this information. The first one is a search engine, and this search is if you want to populate your internal systems. And it's basically you pass the string and you get the number of institutions that it was able to find, that the system was able to find. So for example, in the first example, you see that ETH Zurich, it returns just one ROR ID, where this is actually a real, sorry, this is actually a real affiliation. And this affiliation has two universities in their name. So we need to retrieve both of these institutions. So that's what the search does. Whereas the search top K, it's pretty much when you want user-facing options, and it just retrieves the top K most similar finds. There is one particular thing that regarding the search. So like, for example, here, we retrieve these two ROR IDs because they are parent ROR IDs. But if we were to have Department of Biology University of, or ETH University, the Department of Biology has a ROR ID that is considered like a sub-organization. So we only retrieve that, let's say, ROR ID that's belonging to a sub-organization if we also find the main organization in the string. So that's the relation to each other. So how does it stand, this application, compared to other tools that exist in the market? I think all of them are open source tools. Sorry. So before so all of these results were actually extracted from this paper, the I Feel Good 2024 paper. We just took all of these data sets and we ran our solution against them. And I think we are quite good overall in terms of this landscape. I think the main benefit that our solution brings is the versatility of deploying new versions. So it's very low maintenance because of these two pipelines. For example, OpenAlex has their own solution, but it's based on classification models, which means that every time there is a new registry, which is quite often, they would need to retrain the model. So they predict or infer the latest ROR IDs. What the I Feel Good solution is actually quite identical to ours, but ours is simpler because you can see that they have also a name entity recognition. They have their own vector search or like ranking search, but they have on top of that the LLM to make a decision when they are in certainty. And in our system, we don't need that to deliver almost identical performance. And even 4 out of 7, we perform even better than their solution with something simpler. So is this fast enough for your use case? The search API has a median latency of 350 milliseconds, and in the bulk processing, it can process 1,500 strings per minute. The search top K has a median latency of 300 milliseconds, and it can process 600 strings per minute. The reason the top K it processes less strings per minute is because we create multiple vector points for the same ROR ID. So it means that for us to guarantee the top K answers, we need to fetch a larger number of points and then actually, disambiguate them and so on. Our vector collection has over 565 entries, and currently the embedding model we are using produces a dimension of 1024, a size of 1024. So how does this look for MDPI and integration-wise? How are we using it? I've selected 3 tools or 3 business outputs that we originated from using this tool. The first one is during our submission system, authors need to populate their affiliations. They can copy or they can start typing, and when they do any of these actions, the API is called, and then it starts suggesting the correct ROR ID. And actually, it's quite interesting. In 92% of the times, they select the first option. So it means that the API is actually producing some really good results. I don't have the correct numbers in mind, but we are talking about dozens of thousands of entry points to produce this 92%. So it's not just a couple hundreds of examples. Secondly, Scilit. I don't know if you know, Scilit is a product of MDPI. Is this sort of let's make it simple, like a sort of Google Scholar. It has a lot of all of these publication articles from any publisher. It has a bunch of organizations. It has all of this. It's a very large registry of publication data across publishers, and we are using here to populate a database. So it means that we have articles with authors, with affiliations linked to those authors, and then we map these affiliation strings to ROR IDs. I'm really sorry, I'm recovering from a cold. So before we were using some string matching, and now we are using this, and we actually increased the ROR ID map by 20%, and we are talking that now we have roughly over 90 million affiliation strings with ROR ID map inside of Scilit, among 120 million affiliation strings overall inside Scilit. And then lastly, we have analytics work. So we have other teams that run analytics for dashboards and reporting. Like I was saying, who is publishing with MDPI? What is that trend? And much more detailed reporting. So they are actually calling the API to disambiguate a bunch of affiliation strings to drive this analytics. So how can you actually use it? So we made publicly available this tool. So if you are interested, you can actually use it. So the first option, there is a very simple UI. So if you type ror.mdpi.com, you can try the tool. Small disclaimer about this. The tool was drafted for standard affiliation strings formats. So when you try to use the normal format, and by normal format is if you type in lowercase, you won't get any response, but it's on us. But it's just because our internal data, we never had this issue. So you can give it a try. There is also a freemium API at dev.mdpi.com. So if you have data that you need to process in bulk, you can actually try the API. You can contact us to get an API key. We will be more than happy to give it to you. And then lastly, we open sourced the tool. So if you go to that GitHub, mdpi.ag/ROR search, you can actually get access to the under the hood logic. You can explore it. You can deploy it in your own servers, and you can use, our NER model is hosted on Hugging Face, so you can also pull that. So be more than happy to use it. So that's all for me. Thank you for attending, and happy to hear and have some questions from you. Thank you.
Thank you, Diogo. Now we have time for questions. You want to start?
Hello, thank you very much. I just have a question, like for the embedding, did you use many types? And if yes, which types of embedding it was used?
I think we tried maybe three different models. Yeah, we need to. So the current embedding model we are using was trained by this team. I feel good. They trained their own embedding model tailored for affiliations. It's open source, so we are taking advantage of that. At some point, we really thought of training our own, but there is already a solution that works. We didn't see the benefit of doing that.
Hi. So I usually work as a training coordinator. So I organize stuff like workshops where there are participants who are not just from research institutes, but also from like small startups who might have a same like company name. Would it work out of the box, or does it like one has to collect data to make sure that these small startups which are less known get grouped in the right way?
So I think that's the benefit of using the ROR registry, because it's a community-led initiative. So you could actually suggest, say, all right, maybe we cannot find the ROID for this institute. Does it actually have one? If it doesn't have one, maybe there is, potential to give this information to ROR and say, all right, this institution, you don't have it. Here are the bunch of information, and go through their process of adding this institution to them. And I think that's really the benefit of using these open source tools as much if they are available, right? You already have all of that in ROR. So what I meant to say is that the tool uses what the registry gives us, right? So we are not creating these identifiers. We are just giving them back based on the string information.
Okay, so the institute has to be in the ror.org.
Yes.
Okay.
Yes.
Right. Thank you.
So the registry is updated on a monthly basis, roughly. So there is really a lot of new institutions at every month and corrections. So I would assume it's very kept up to date, and also because it's maintained by three major players in the publication industry. The first one is Crossref, the second one is DataCite, and I don't remember the third one. But it's renowned organizations that are maintaining the ROR ID.
Do we have other questions? If not, thanks, Diego again. Thank you. We'll start next talk in 10 minutes. Yeah, it's 10 minutes break. Are you okay? Yeah. It's not comfortable to talk when you yeah. But it was good.
I don't choose when I get sick, right?
Okay. Sure. Yeah. So, you know, like, Arab. Well, I found it. But even like, you know, so that specific, okay. No, I don't know. Yeah, and like this one. Alphabet. And German. What does that say? It doesn't equal to. Depends what is your language. Or not language, because for some people, one language is to do to them. Yeah. Yeah, it's. Previously, it was coffee, so it's changed. Yeah.
Yes, I think.
Yeah, we have. What do you need? What do you need? Yeah. Okay. Yeah. We have a
Wow. I wish this is like voice control. And then you see all my screens and my amazing.
Are you connected already?
I'm connected, but 1 second, because now people are seeing all my emails.
No, we don't see anything right now. So let's set up, and then I will, I will enable here. No worries. Let me know when you're ready. No worries. Yeah, we have a mic because everything is recorded. So, are we okay?
Yes.
Okay. And this is your mic.
Thank you. 5 minutes until I have to get out. 5 minutes until can I? Okay, good. Okay, good. Thanks. I'm on time, right? Let me know when I should start. Good. Yes.
Yeah. I think we are just on time. Thank you. So.
So I'm not the latest one. So good.
Yeah. Yeah. Please welcome our next speaker.
thank you. Yeah, so actually I've given this talk last week at EuroPython. So if you have here in EuroPython, I'm sorry, I only added one slide. So if that slides, I hope that slides will interest you. Otherwise, you have heard this before. However, I guess that this crowd is slightly different than the EuroPython crowd because maybe let me know how many of you are actually researchers. Perfect. Then I think you are my crowd. So that's good. Cool. So while people are sitting down, let's get started. If this works, if it doesn't work, then I can do this. Cool. So I think I don't need to explain too much about high performance computing. If you are a researcher, you probably like if you're doing some computational research, you probably have already. It's okay. I don't need it. So yeah, so you already know that when you are doing a lot of calculation, right? Like so for example, my background is actually computational physics. So I was studying some quantum mechanics things. I also like help. So at that time, I will write a program and then like send to the cluster, and then we at that time in my university, that was quite a while ago. I'm actually older than I look. So like so we'll be like, we have the best clusters in Asia or something like that. So and then like go for coffee, or like my friend will play Diablo 2. That's what he do, and then like until the result is done, right? So that's what happened. The reason why we have the cluster is because like a lot of computation actually require more computational power than a single computer can handle. At that time, of course, a single computer is not like this, right? Probably this one will beat the cluster back in the day. So the benefit of it is that the computation can be handled by different machines. So it can handle, in parallel, which is something that we want, and that's why like the cluster or like the HPC is born. So one of the things that I should mention, I forgot which slides I put that in, but I need to mention is that the focus today, I won't be focusing on like your proper like cluster or like Hadoop or all this like. I'm more about like doing parallel computing in a single machine. Nowadays, like a machine is so good that some people actually like use similar HPC technique, but actually run on a single computer. It's just that because computer now have multiple core, so you can still do things in parallel. So just not to make it super confusing for people. It's like, but that's not. But anyway, so let's focus on that. So I don't think, again, like I don't think this. If you are already in the research institute, you already know this. A lot, like especially something that is different from back in my time, is that like now we have lots of data. So like not just that, maybe in the past mostly it's like for some like simulation experiment, you do it in maybe linear algebra. That's what I do with. Back in the time, a lot of times. Nowadays, like you also have other things that are super like computational heavy. For example, handling a lot of data. So a large data set, even if you do something like very simple, if you have a lot of data, it will actually cost a lot of time. And now, of course, we also have AI, machine learning. Like again, like AI is like deep learning is also linear algebra. So that's yay, we love that. So yeah, lots of computing need to be done. So right, so application, again, research, but also like weather modeling is super important these days. We know we have an El Nino this year, so yeah, predicting weather super important. And then again, like research, finance modeling. This is something that like a lot of my research peer back in the time, they now earn a lot of money because they switched to do like instead of calculating physics, which nobody cares, they calculate like stock market. So now they make a lot of money. So that's something that you can apply your skills that you learn during your research years. Like AI again, like where the big money is, right? So however, all these people, like I remember, well, back at the time, if you are like people who focus on doing this, you have to like just like grind your teeth and learn C++, whatever the programming language that you are required to create those programs, which I would say not the most fun to write. I guess like if we are all sitting here, we all love writing in Python. The benefit of Python is that like Python is very fast in coding. Like for someone who want to like learn, like for example, they have something they want to do, they learn Python. From learning Python to like writing a program that works very fast. However, Python was known to be very slow in execution because back in the time when Python was born, you know, again, like unless you are in a university, you won't have like you don't have a cluster. You probably won't do any parallel processing if you have a modest computer. So at that time, the design of Python was very like, you know, the genius of Python is that we use a GIL. We just like GIL is basically a mutex, a global interpreter log that makes sure that everything, like all the only one thread is processed at a time. So there's no true parallel processing happening, which have some benefit back in the time while most people are not doing parallel processing. That make things way easier to be programmed, and there's less you know, prone to error. So which is great. However, today, or actually like already like 10, 20 years ago, people found it quite limiting because what if I want to do all these amazing things, right? Like a lot of researcher, they were doing this. They need a tool that can make like let them work really fast to code, but they are not programmers, so they don't want to learn C or like just to do this. So they discovered Python, they used Python, however, Python was not fast enough. So at that time, there are some like, you know, really, really clever people. So some of the big names you've heard, like Travis, you know, the creator of NumPy, and they actually invented these libraries that actually use a C extension that can handle the low-level calculation with C, but the surface of it, so for the user, they're actually writing in Python. The way to do it is that because Python is an interpreted language, is actually interpreted by a interpreter, let's call it CPython, which is the standard one actually. So CPython will provide some C API in case you want to connect some binary executable pieces to it. You can do that. And NumPy actually take advantage of that. So a lot of the bottleneck, the slow calculation bits were not done in Python. So they can be really, really fast. Yeah, so yeah, I think my slides are quite like mumbo jumbo. I'm not very good at that, sorry. But again, like it's talking about like with C and C++, right? So now, you know, we can have something that is very easy to code, but when it executes, it's really fast. However, you see the third party here that's called Rust. Who haven't heard of Rust? Okay, one person, two persons. Okay, Rust is a new programming language. Just I would say that it's on the same level as C and C++. So it has allow you to write code that have more control at that level. You know, Python is kind of like at the very surface level, right? Like it doesn't handle all these like, you know, memory allocation, all these like pointer, like Python. Most of the Python users don't do that. However, if you have learned a bit of C and C++, you'll be like, oh my god, I hate pointers. So yeah, so Rust also have those. Rust have smart pointers, which is even better. However, it's kind of like a tool that is like kind of bridging that gap between like I want a tool that can code very easily, and another side is like I want things to be like really I have full control of how my computer is working. I want it to work in parallel, do something really, really fast, and use more resources, whatever. So now we have two things. How do we connect them, right? In the past, we have those libraries, NumPy, and you know, and actually a lot of libraries use NumPy, but maybe PyTorch. PyTorch also will have some. Imagine you have to. You know, imagine PyTorch is purely written in Python. Like, I don't think you can do any deep learning at all. So, yeah, so these are the libraries that actually have that extension that can let you, again, like add those pieces that are faster for Python. So let's look at what they are made of, right? So not surprising, you know, NumPy, a lot of Python. However, you can see that there are other languages there. Fortran is I have been told that Fortran will be there forever, even though like the maintainers like was like, oh, we don't like Fortran, but they are staying. So well done, it's 0.2% still there. C++ and C, actually mostly C, are now there. Python, again, like I know the Python maintainer is somewhere around in this conference. Python is another very, very good, programming language to, make maintaining all these pieces very easily. So yeah, that's the combination. So wow, C has a role here. So SciPy, SciPy is again like with that, but they use a little bit more Python, which is good because Python. What is Python, right? Like okay, explain a little bit. Yeah, give them some love. Python is actually very similar to Python because it's a superset of Python. However, so it's very easy to write for Python programmers. However, using Python, you can kind of achieve some performance comparable to C. So it's kind of like, it's good. Of course, if you want to like do, again, like have full control, you have to really do C. But Python is kind of provide a way for people who are familiar with Python, don't want to learn C, have, an extra tool that they can do. So, so imagine if you contribute to SciPy, it would be way easier because you just need to write Python. Maybe you don't want to touch that bit, so you just Python and Python mainly. So that's quite good. Okay, PyTorch. PyTorch is actually mostly, so this is a different combination, right? Also some C hanging around. They need CUDA because, of course, a lot of deep learning use and deep learning AI, deep learning. Nowadays, people just use the term AI, right? They don't say deep learning. Okay, AI use a lot of CUDA, like they use GPU, so they need CUDA to communicate with the GPU, but they're heavy on C++. I have talked to some people, they actually like favor C++ over C, which is fair. So it's another way of adding the binary extension to Python, and we all use it, so good. This is the interesting one. This is the one, Polars. I'm sure all of you have heard about Polars, right? Shout if you don't know what is Polars, not the animal. So Polars is using a lot of Rust. See, because Polars is quite a new library. Polars is I think I can't remember when Polars. I think it's like maybe 2017 was spawned. Compared to these others, this is quite young. So they're using mostly Rust. No C, no C++, no Python, sorry. But yeah, so this is actually becoming the trend in the Python community right now. So what happened? Now I think I've heard, because I was doing Rust Summit last week. So David Huey, the maintainer of PyL3, said that like now Rust is part of the Python ecosystem. Wow, big claim. So what, like, how do we get here? Where does it start? So in 2015, Rust 1.0 was officially released. If you have done some program development, 1.0 is usually the first stable version that people can use. If it's 0, that means it's still experimental. So Rust was born, kind of. And then 2017, PyL3 was found. So PyL3 is a very important project. I would give you more information later. So PyL3 was founded, but at that time, everything is still like kind of in like design. So it's like still just kind of in a baby stage. In 2019, that's around the time that I mentioned one of the superhero, David Huey, who is the maintainer of PyL3 today. He started joining the development of PyL3, and it really speed up everything. And then in 2020, so PyL3 have achieved a compilation on stable Rust. So it seems like in 2020, everything is ready to use. PyL3 was the glue gluing Rust and Python together. PyL3 is so I will explain what PyL3 is, but however, so with Rust being stable and people love it, usable, good, and PyL3 also stable, usable, now it seems like we are ready to use Rust as a binary extension for Python. So in 2021, big thing happened. Cryptography, who know the cryptography library? You know cryptography library, right? Yeah, so cryptography library is very important because a lot of web application, they are sending information around. They need to be, not cryptocurrency. They need to be, code in a way that's like, encoded, so it's like secret, so nobody can like, spy on what you are sending the other person. That's how internet works, right? So it's a very important library. They started switch from its core from C to Rust. I'm talking about this is the Python library, right? Python also have a lot of users. They are building web application, and then down the dependency line, that will be cryptography. And now these packages, one of the most important packages in the Python ecosystem, switch their core, which is, like I said, a lot of this library, their core actually is built from other libraries because they need that for the computational power. They switch from C to Rust. Bold move, a lot of controversies in the community. I think mostly, it's just my speculation, right? I think mostly because people who are maintaining it at that time, they are all like expert in C, and then they're like, if we switch to Rust, we have to learn a new programming language, right? Like so big controversy, very bold move. I will also explain why they make that move in a bit later. So they did that, and then nothing happened. Everything works well, good. So now everybody see that, and it's like, yay, let's do that. Let's just copy them and do that. So that's the Rustnaissance. That's the term that a lot of community members jokingly use. A lot of Python tools are now written in Rust. They're fast. So to name some of them, like UV, Rough, and any others that you know. Yep. Any? Pixie, Pyrefly, Polars. I'll just show you. So a lot of Python tooling that like people starting to realize, oh, that's like the same thing, but fast and good. So like that's around that time they start popping up everywhere. Which is like, okay, now whenever you see that, I was like, but why we don't rewrite CPython in Rust, right? Okay, actually, I was just a little bit clickbaiting because Rust in CPython project is not rewriting CPython in Rust, but it's a kind of experimental project that so it's led by one of the core team member who is like leading this is Emma. She is leading this to see where there are like some bottleneck pieces of CPython can be actually benefit from switching it to Rust. So it won't be rewriting everything at the beginning. So I've heard the presentation at the Rust Summit. So at the beginning, it will be zlib, that the standard library would be the first, would be the candidate to be experiment on, to be switching to Rust. So I do know that they are drafting a PEP, so maybe it will come out later, and then you will have more official information once it's out. So pay attention to the news. So again, like what's PyO3, right? I mentioned that a little bit before. PyO3 is a very important pieces in this like Rustnaissance because PyO3, so PyO3 itself is a Rust crate. So what are crates, right? Crates are actually in Rust terms are something similar to a library or a module, right? So you can you don't have to reinvent the code. You can share it between other people. So so it's actually a Rust crate, so you can just use it. It's open source. So it's actually like I would say they do some black magic that let you create a Python extension entirely in Rust, and it looks really, really like Python. So I will show you the code a bit like at the end of this session. You'll see like, oh, that's not too hard. I can write Rust code. that's how easy it is, right? So so yeah, like if you let's say if you have so for example Polars, I use Polars as an example. Polar itself, Polar RS is actually a Rust crate. So Polar itself is actually like originally a Rust library. However, the creator have this like insight of like, oh, why don't we benefit the Python community by giving like wrapping it using PyO3 become a Python library that everybody in the Python side can also use, right? So that's yeah, so that's the the power of PyO3. It can change, well, it more or less change a Rust crate into a Python library. So so another thing is that like PyO3 also supports some native Python module, so and also enabling the Python interpreter in a Rust application. So it's not just you can create a Python module and class and object using Rust code. You can actually manipulate a Python object or call a Python object or kind of attach to the Python interpreter in your Rust application. So it's not just one way, like from Rust to Python, but also like from Python to Rust. It really is a bridge. It's a two-way bridge. And the good thing about it is that, like I explained before, if you see the code, it will be like, this is so easy. Why don't I do Rust? Because it it kind of hides a lot of complication that like, so if you, let's say you write a Python like extension in C, you have a lot of complication, right? Because Python is so simple. It keeps a lot of like low-level things like hidden away. So Python GUI is one thing. You have to handle it because this is unique to Python. You have to always, if the Python GUI exists, what are you going to do with it? There's also like Python exception handling. Again, like this is very unique to Python. You have to handle it. Type conversions. Python have a very, very flexible kind of type. If it's in another language, how do you handle that? Also, reference counting, a lot of things that Python developers or researchers using Python don't care about. They are all like hidden away when you use pure Python. And PyO3 try to also take care of those complexity for you when you're crossing the bridge. So right now, there are some experimental support for async and away. However, it's not a finished product. It needs a lot of love. In the Rust Summit, David, the maintainer, called for some love for it. So if you think that you want to give it some love, then let me know. I would, introduce you to the project. So yeah, and you will see how we can write, create a Python module and object with Rust. So this is the example I copied from the PyO3 user guide. This code, okay, like you have to set up a little bit. You have to, of course, have Rust and Cargo, which is a 2 chain for Rust. However, if you set everything up and then you just run this, so this, like, first of all, this looks very like a Python, right? In a module, you have like a function, and then this one with Maturin, which is another tool that in the PyO3 project, then this will become a Python library that you can import. So this is how simple and elegant it is. It takes a lot of work, like I said, from 2019 actually is that until today. Like this has changed a lot, and every step we are trying to make it more easy for Python developers. So again, like if you're maintaining a library that's written in, Rust using PyO3, at least this part you won't have to pull your hair out, right? Otherwise, nobody's going to do it. So I mentioned Maturin a little bit. So Maturin is another very important tool that works together with PyO3. Maturin is actually like it works in the command line. It's a command line tool. So it makes everything very simple. So for example, if you're not familiar with a Rust project, you don't know where things are sitting, you can just use Maturin init, which will build you a skeleton of your PyO3 project for you. And after you have written some code, you can just in your command line type Maturin develop, and then it will kind of oh my god, I'm running out of time. And compile, a little bit like it will compile, and then now you can use it. Provide all these tools. You can even publish to PyBI with Maturin, so it's good, right? But Rust, right? Like everything has been fine until now. Why we just keep using C and C++? Well, because Rust is actually very good. I love it. It's have very comparable performance with C and C++. However, it doesn't have the downside of C and C++, which is like, this undefined behavior, null pointers, those things that people hate. It's memory safe and thread safe by default. So that's good. It also provides a very good ecosystem. I will show you like there are some like crates that is quite useful for HPC. But also one thing that I really love is Cargo. So Cargo is a tool that comes together with Rust by default. So with Cargo, you can do everything. You know Python, right? We have all these different tools, or even like, C, we have the CMake and all this. Like Rust, everybody just use Cargo and everything is fine. I can't go into the detail. I don't have time, but very nice. Integration, like I mentioned, Power3 and Maturin make things super easy and easy to rewrite your code. These are the crates that actually they are Rust crates, and they are quite useful in HPC. You can see like some calculation thing, some parallelization thing, memory parallelism, even CUDA, GPU, like, you have something for it. So that's great. Right. So again, I'm now like doing sales pitch, right? Like why choose Rust, right? Like I said, memory safety, because Rust, if you're learning Rust, you know this like weird thing that's called ownership thing. It's there because it can make sure that it's memory safe by default. So that's good. And there's another thing that the Rust community really love are the fearless concurrency, which means that there are some like tools that's provided, for example, the send and sync trait, the messaging channel, the arc mutex, and atomic types. These are all tools you can use to do some like parallel programming, right? So, and all those tools help you to avoid those like hiccups, like, race conditions, like memory leak and all those things. And also no undefined behaviors. I already say like no null pointers, no problem. Unified tooling, you don't have to, wrangle with the CMake, like, the C++ like make files and this. Cargo take care of everything from formatting your code to, compiling, building, checking, expanding your macro, everything is just Cargo something, right? So it's good. It's also a package manager as well. So, right, cool. So you may ask, right? Okay, I am ready to switch to Rust, but I need NumPy to survive. Is there anything equivalent? Well, there are some suggestions here. You can have a look. However, of course, they won't be identical. You may have some like cases that's like, oh, this can't do. But I would suggest just have a look. And then if you have some bottleneck code, maybe you can think about switching to Rust and then use Power3 to, connect it back to Python. So last thing, I don't have that much time, but I want you to remember these three things. First, keep using Python, right? Python is good. Python is good because it's very easy to code. Although it has its downfall, but the community has gone through a long way to overcome all these problems. Like, for example, providing a lot of binary extensions and libraries that can do good stuff. However, the community discovered that Rust have some advantage. And also Rust becoming a very highly desired and loved language for the younger generation. So because they have a lot of good things, and people are now maybe they're switching to Rust. And other thing is that please show some love to my favorite library, Power3 and Maturin, because they are very important bridging the two. There's also, I remember some questions in the Rust Summit. Will Power3 become part of the Rust in C Python project? Who knows? Maybe if that project went well and then we would get more, we want more Rust in Python, then maybe that would be huge, right? So please show some love to Power3 and Rust. So learning resources. So I hope I convinced you. If you want to learn more, these are the very good place to start. If you want the slides, I have the QR code there for you. I should also share it on Discord. I forgot in EuroPython, which I will do it as well after this talk. Please check it out. And, I love learning new things. I hope you do too. that's it. So thank you so much. We can also connect if you want to be friends with me. And thank you for your patience and enjoy the conference.
Thank you, Dr. Tinghoff, for a very interesting talk. Now we have time for questions.
So if I suggest to colleagues maintaining my library that maybe we should replace some Python code with some Rust code, and they go, "Oh, why the hell should we do that?" Can you give me a very short answer for them?
Well, I don't want to say too many bad things about Python because I think because let's be honest, like when I started Python, I love Python. I remember joining the sprints as Python, although at that time I don't have the ability to do much useful contribution, but I do enjoy the sprint and learn about Python. I think if I have to convince people that like, oh, Rust is the future, switch to Rust, it would be you can take benefit of what the Rust community is building for us, right? For Python, you have to still maintain the code yourself. Yes, you don't have to learn a new thing. It's way easier. However, if let's say you want to add something to your library and then Rust already have something that can do it and do it fast, maybe it exists in Python, but the Python equivalent maybe not as fast. And that Rust library crate does not have, they don't plan to, wrap it with Power Free and it's not like Polus, right? You can use it in Python. Then someone needs to do it, maybe you. So yeah, and I think a lot of people, they switch to Rust is because they really love the benefit of memory safety, and also like, doing all these fearless concurrency thing. It's very hard to explain to you like why people love Rust in such a short time. I would suggest, I love learning new things. Have a look, see if that's something for you. It's okay if it's not, keep using Python. Python is awesome, but explore the new world. See if that could be something that you will be switching to one day.
Okay. Hello. Thank you very much. I just like you mentioned about Kaggle. So for me, like Kaggle, I only like collect from it data sets to train on it some other. So I don't understand like the relationship between Kaggle and the Rust.
Right. Kaggle is kind of, imagine you have pip and black and many other things in one place. Why Rust need Kaggle is because Rust is different from Python. Python is an interpret language. So if you have Python installed on your computer, your Python code will work. In Rust or C or other compiled language, you have to first compile your code. It will become a binary, and then that binary will work. So Kaggle also acts as a compiler. And then because you have to compile your code, there's also a lot of things you need to do before compiling, like checking, like expanding the macro and all those things. So those Kaggle also provide. But I think the most obvious thing for a Python user to see what Kaggle's role is that imagine it's a pip plus setup tool plus many other like flag and many other things. And you can't. It will be a nightmare if you don't have Kaggle and you try to do Rust. Let's put it that way. Yeah.
Just captivated by your animation while I'm sitting here.
Sorry. Yeah.
So
yeah.
You know a little bit about our use case, but for the room, Markov is becoming the standard for connecting quantum computers to HPCs. And we have this very problem. If you're in my shoes, in terms of knowing that the audiences are growing one way or the other, would you pick C or would you be picking Rust in terms of availability of talent over time?
Oh, I mean, like today, when you start today, definitely Rust. Not because I love Rust, it's because Rust. I think a lot of people they know C as well, but they discover that Rust is way easier to maintain than C, because of all these like memory problems that like C actually like prone to a lot of vulnerability because, you know, again, like Rust is memory safe by default. If you don't use a magic word called unsafe in Rust, then it's in theory it's memory safe. So if you imagine you have to maintain this library and then, you know, it's open source and people contribute to it, you want it to be as secure and as less likely to F up as possible. So Rust will have that benefit. And I know a lot of corporation also like starting to invest in Rust and moving towards Rust. So if you start today, I would say that Rust would be a better choice. Although I know like it's just like Fortran, right? Like C will still be hanging in like, you know, here and there and everywhere. But let's hopefully like there will be less and less need to maintain C code. Yeah.
I'm sold. I'll buy 10. You're compelling. Thank you.
Okay, thank you. Thank you once again for your talk. And yeah, we'll give a round of applause. And we're not finished for today. You're welcome to join in our main room. We have announcement of posters, so there will be a presentation of posters that we have in a room behind us. So please move to the other room.
Thank you very much. I think maybe the short version for me would be the parallel processing bit, because in the moment our library's a bit weak on that, and maybe we could try something with Rust.
I free fed the bill, and I think now I'll